Today I discuss one important topics related to measure theory. Okay, one important topics related to measure theory, which is specially related to measurable function. Okay, one function when be measurable we talk about now. This one is easy, but we also discuss this one to further procedure of measure theory. That means we have to extend measure theory. We have to extend some discussion about measure theory. We have to talk about that. So we are now discuss this proposition. Okay, let f be an extended real function whose domain is measurable, and then the following statements are equivalent. For each alpha belongs to R, the set x fx greater than alpha is measurable. And now we talk about here, for each alpha belongs to R, the set x such that fx less than alpha, okay, or fx here greater than equal to alpha is measurable. Okay, then we now talk about number 3. For each alpha belongs to R, the set x such that fx less than alpha is measurable. Okay, and again we talk about another number 4. Number 4 we also talk about here. For each alpha belongs to R, the set x such that fx less than equal to alpha is measurable. Okay, now number 5. For each extended real number alpha, the set x fx equal to alpha is measurable. For each extended real number alpha, the set x such that fx equal to alpha be measurable. Okay, now we're going to discussion about the proof of this theorem. Okay, this one are too easy, obviously important for us, because we also discuss another theorem. Then this one is gives very important tool to prove another theorem. Okay, so today we now discuss this one. So we start about proof here. We write this proof now. Let the domain of A be D. Let the domain of A be D. Okay. Then what? Then we have first 1 implies 2, or first implies second. Okay. Then what we have to do, since we know about that, okay, here we get some mistake. We not talk about 2 here. 1 implies 4 first. Okay, because 1 and 4 are related to each other, so we talk about 1 implies 4. Okay, then since x equal to x fx less than equal to alpha equal to d difference x such that fx greater than alpha. Okay, this one is possible or not possible. Now we erase our portion and going to further discussion of that. Okay, then the difference of two measurable set is measurable. We first talk about that. We know about its A difference B. If AB is measurable, then A difference B is measurable. We also known about it in previous class. So now we also just apply this. The difference between two measurable sets be measurable. Okay. Then we also talk about this one now. This set x fx greater than alpha, if this one measurable, if this be measurable, then obviously this x fx less than equal to alpha be measurable. Okay. Now similarly we also discuss another portion. Okay, that means 4 implies 1. How we talk about this one? Okay, 4 implies 1 in this way. Same 4 implies 1. We also talk about same way. That means just we talk if x greater than alpha equal to d difference x such that fx less than equal to alpha. Then if this one measurable, then this one is measurable. Okay, so 4 implies 1 is done. Now we're going to 2 implies 3. Okay, so similarly this one happened. 2 implies 3. There this one x fx here less than alpha equal to d difference x fx greater than equal to alpha. Okay. Oh, why here some problem occur, I don't know. Who created this problem, I also don't know. But they are really four thinker and create obstacle around my path. I'll decide that now. Now this one is okay. We'll also start about it. Okay, x such that fx less than alpha equal to d difference this one. Then this if this one is measurable, then this one is measurable. Again 3 implies 2 is done if x such that fx greater than equal to alpha equal to d difference x such that fx less than alpha. This one obviously possible. Okay, so this type of proofs are easily or handle this one. Okay, now we're going to further discussion about that. We'll erase that portion now. Here 1 implies 2. Okay, 1 implies 2 since x such that fx less than alpha. Okay, this one equal to what? This one less than or greater than equal to alpha. Okay, greater than equal to alpha. That means here we also talk about if x greater than alpha is, that means measurable, then we have to decide greater than equal to alpha. Then what we done? Intersection of n equal to 1 to infinity this x such that fx greater than equal to alpha difference on y. Okay, this one, if this one is, that means equal to, or here the less greater than is possible. Okay, then the intersection of a sequence of measurable set is measurable. The intersection, we know about that if a b are measurable, then a intersection b is also measurable. So the intersection of measurable sets be measurable. Then x such that fx greater than alpha be measurable. Okay. Similarly, 2 implies 1. Okay. Since x such that fx greater than alpha equal to what? Equal to union of, okay, greater than, not 2 implies 1, obviously greater than, equal to union of n equal to 1 to infinity x such that fx greater than equal to alpha difference 1 by n. Okay, alpha plus 1 by n. Then what happened? This one, union of this equal to fx greater than alpha. Okay, then what we get? The union of measurable sets be measurable. We know about that if a b belongs to measurable, then union of measurable set be measurable. Then what happened? Then obviously we get this conclusion. Okay, that means this implies that then this one x such that fx greater than alpha be measurable. In this way we talk about this one. That means 1 implies 2, 2 implies 1. Obviously in this way we also discuss another one. Okay, now we're going to this proof of 5. Okay, how we discuss proof of 5? If alpha belongs to R, then what happened? Then here we write x such that fx equal to alpha equal to, here x such that fx greater than equal to alpha intersection x such that fx less than equal to alpha. Okay, then obviously this one is measurable and this one is measurable, so this one is obviously measurable. Okay, since x such that fx greater than equal to alpha and x such that fx less than equal to alpha be measurable, then x such that fx equal to alpha be measurable. Okay, now we're going to be discussion of another way how we discuss this. Okay, where is that portion? Okay, then this one is implies that if this one be a measurable set, okay, then this one is measurable. Okay, then we also talk about if this one, that means if fx greater than, if alpha is not real number, that means alpha equal to plus infinity, then this one is possible. If alpha equal to minus infinity, then what happen? Then we talk about x such that fx equal to minus infinity, then equal to what? Then that means we talk about here x such that fx less than equal to n. Okay, 1 2 3 dot 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 here, that means intersection of n equal to 1 to infinity. Okay, no, not here, n equal to minus infinity to 2. Okay, fx less than equal to minus infinity to here 0. Okay, then this one be possible. Okay, that means minus infinity, then this one, then we talk about fx equal this one equal to this, and obviously this one happen. Okay, if x equal to minus infinity, then here if 1 2 3, then fx greater than infinity intersection equal to, and here here 0 minus 1 minus 2 and minus infinity is the intersection. Okay, in this way we also discuss this one. So if I, that means change this one, then n equal to 0 to infinity, here minus n. Okay, 0 minus 1 minus 2 minus 3 dot dot dot. In this way we also discuss this one. Okay, this one also possible, less than equal to minus n, then obviously we get this one. Then obviously we talk about that intersection of measurable sets is measurable if this one is not equal to 5, then obviously this set is measurable. This one are measurable, this one are measurable. Why? Because intersection of this one is measurable sets. Okay, now we also going to another similar proposition. Okay, this one also too easy, but we also talk about that now. We also discuss this easy principles. Okay, first, then we also going to further discussion of that. Okay, so we write this proposition here. Let c be a constant, let c be a constant. Fg, let Fg be two measurable, Fg be two measurable real valued function defined on the same domain. Then the function f plus c and cf and f plus g and g difference f and fg are also measurable. Are also measurable. Okay, so we also discuss this one now. Okay, this one also one easy, that means principle. How we discuss this one? Here we know about that if, that means a plus c. Okay, we know about that x such that fx plus c less than alpha equal to x such that fx less than alpha difference c. Okay, so f plus c, so a plus c be measurable if a be measurable. Since c belongs to R and alpha difference c belongs to R. Okay, now we also talk about same problem. Here x such that cfx less than alpha, then x such that fx less than alpha by c. Okay, where c belongs to R and alpha belongs to R and c not equal to 0. Then what happened? Then this one, if f is measurable, then cf is measurable. So cf be measurable if f be measurable. Okay, now we talk about another topics. We also erase that one. Now we're going to f plus g, g minus f, this one. Okay, so we erase whole portion and going to further discussion about that. Now here, if fx plus gx less than alpha, okay, then fx less than alpha difference gx, then 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 axiom of Archimedes, there is a rational number, then y axiom of Archimedes. Okay, there exists R belongs to Q what happened such that if x less than r less than alpha difference gx. Okay, hence x such that if x plus gx less than alpha equal to union of x such that if x less than r, okay, and intersection of x such that gx less than alpha difference r. Okay, then what we get, then since the rationals are countable, then we talk about it now. Since the rational are countable, but since the rational are countable, we write this one now. Since the rationals are countable, rationals are countable, since the rationals are countable, this should be measurable. So a plus g be measurable. Okay, now again we also go to this process. Okay, so here what we talk, just fx plus gx less than alpha, then fx less than alpha difference gx, and the y axiom of Archimedes, there exists r belongs to q such that fx less than r less than alpha difference gx. Hence x such that fx plus gx less than alpha equal to union of x such that fx less than r and gx less than alpha difference r. Okay, then what happened, then here since the rational are countable, then these sets be measurable. Okay, so f plus c is measurable. Next we talk about similarly also done this one. Since minus g is equal to minus 1 multiplied by z is measurable when g be measurable, so we have f difference g be measurable. Okay, that means here a plus g is measurable, so we talk about in this way. Since this one, that means a plus g equal to a plus g measurable, a minus g equal to what, a plus minus 1 dot c. Okay, so this one be measurable. Okay, then we now going to another discussion of that means f square is measurable or not. Okay, we erase that portion and going to further discussion of that. Here the function f square, the function f square be measurable. Okay, since x such that f square is less than alpha or greater than alpha equal to x such that fx greater than square root of alpha union x such that fx less than square root of alpha. Difference here minus this one. Okay, and then what happened? Then here for alpha greater than equal to 0. Okay, so what happened? This one equal to d if alpha greater than 0. Okay, alpha greater than 0, this one is possible, and if alpha less than 0, then we talk about this alpha remains same. Okay, this one d if alpha less than 0. So d is the domain of where d is the domain of f, where d be the domain of f, domain d be the domain of f. Okay, thus we also done this one. That means f square is measurable. Okay, since two measurable union of function is measurable, and here obviously if alpha is less than 0, okay, then this one obviously domain of f x such that f square greater than alpha equal to d. Okay, then obviously we talk about that the function f square be measurable. Now what we done here, again we talk about here, thus fg equal to what? Half of f plus g whole square difference f square difference g square. Okay, then what we get? We know about that f plus g measurable. So f plus g whole square be measurable, and f square and g square are measurable. So fg be measurable. Okay, so fg be measurable. Okay, now we also talk about further discussion of something. Okay, but today I'll stop here.